So I'm going to tell you today about work that we've done over the past 10 or 15 years that grew out of work on systems biology and cell dynamics, where we were trying to write one of these systems biology models, and we had 48 parameters, and I'll tell you about that in a little while. But we discovered something very weird about our multi-parameter fit to data. And then we discovered, and that was basically that it was sloppy, that there were some directions in parameter space that were important for the fit, that you could change the parameters and you would get a significant change. But there are certain parameter combinations, in fact, most parameter combinations, most directions in parameter space, there were a large number of directions in parameter space that you could change that combination of parameters many orders of magnitude and not change the behavior. And we ended up deciding that that was important for the success of our modeling, that we didn't know what the parameters were, but we could still make predictions. And I'll tell you about that later. And then we started looking in much more general contexts and saw that many other systems were sloppy. So for example, our model of the early universe, when fit to microwave background radiation data, is also sloppy in very much the same way. And then I will tell you something about differential geometry and how we understand sloppiness in terms of differential geometry and a kind of interpolation theory. But, and then recently, and I'm going to start with this in the talk, recently we've come to the conclusion that the same phenomenon, that some degrees of freedom, combinations of degrees of freedom are important and most are unimportant, underlies science much more broadly. So I'm going to start this talk at the end with our most recent work on connecting what I'm going to call sloppiness to physics.
Jim,
yes?
Does this have anything to do with what people in engineering or applied maths call global sensitivity analysis?
I don't know. I don't know anything about global stability analysis.
Models with many parameters, and you try to know which parameters are important?
It could be. I would like to know more. You're the first person that's ever mentioned it to me. So here's a least squares fit to data. You have radioactive decay. It's a standard problem in physics where people say, with 4 parameters I can fit an elephant. And it's actually kind of perverse that you actually can't fit most time series with decaying exponentials. It has to be monotone decreasing and a bunch of other things. But it is true that it's very difficult to extract the radioactive decay exponents out of the exponents or the amplitudes out of this decay, that you can fit the data very nicely. And in fact, you can make predictions for interpolations, but if you try to extrapolate very far, of course, you get large errors. And in a sense, most of this talk is going to be in the same vein. When can you, what kinds of information can you extract out of physical systems that are kind of interpolations between existing knowledge, and what things are extrapolations. And there's going to be this this general picture of a best fit in some large dimensional parameter space. Contours of bad fits worse and worse as you go out. The idea of sampling the parameters that do a reasonable job of fitting the data to get ideas about how bad your data fits are, and the distinction between bare parameters and what we'll sometimes call eigenparameters. Those parameter combinations that are aligned with the sloppy and stiff directions. And I want to emphasize, I'm not saying that the systems are robust in the biological sense, or that there are certain parameters that just don't matter. All the parameters will end up mattering, all the bare parameters will end up mattering. The physics we're describing is combinations of parameters can be exchanged for one another and not change the observed behavior, not change the behavior you're interested in.
Are you assuming there are good minimum? I mean,
no, actually, because of the sloppiness, there will be a wide variety of minima that are far away, nearly perfect fits that are far away in parameter space. And most people naively would say those are bad fits, but they're good fits. They're just bad parameters, and they can sometimes make good predictions. And why is that? So this is an example of, you remember, this is supposed to be tilted in some weird direction in parameter space. So these are the bare parameter axes I'm drawing on here that are rotated. But I've just plotted the second stiffest direction of a problem with fitting exponentials against the second sloppiest, the sloppiest direction against the second stiffest. And you can see you have this long, narrow ellipse, and you have a sloppy direction, a stiff direction, and what you haven't noticed is the axes on this plot. The axes here are 1,000 times the axes here. That is to say, for this particular set of parameters, which is for this number of exponentials, it's been tuned to look like our systems biology model. This direction should be stretched out to about 1 kilometer. Okay, so there's a dramatic separation between the stiff and sloppy directions in multi-parameter fits. And so the eigenvalues about this best fit for the eigenparameters are spread out over many orders of magnitude. Never in one board. So the caricature we're going to have is that there's a parameter space and a behavior space. And the parameter space, if I take a circle of parameters, I get a very strongly stretched region in data space, with the sloppy directions ending up being very narrow in data space, in behavior space. And if I take a range of behaviors, it corresponds to a very stretched region in parameter space, with the sloppy directions being the one that's spread out, because to make a small change in behavior in a sloppy direction, I have to make a large change in parameters. Yes?
Do you need a scale to tell me if that's large or not? Because when you say 10 to the minus 3 or 10 to the minus 6, if I have physical units, that could just be the same.
So that bothered us for many years, and that will lead us into a new way of thinking about it, in which parameter space is boring and we will start ignoring it. We will focus on data space. Data space is a natural metric. So what he's pointing out is an important question. There's no natural metric in parameter space. Or there can be a natural metric, but typically there isn't.
Yeah.
That a Michaelis-Menten constant and a binding rate have different units, and you could change units and change everything. So most of the time, most of us will try to put things in sort of natural units to try to keep things in order 1, and that's very useful. And all of our early work was relying on human beings picking sensible units. However, I did point out there was a range of 10 to the 6th or 10 to the 12th, and you would have to make very perverse units in most cases to stretch out the directions that much. And so we, roughly speaking, relied on sensible choices of units. Now we managed to come up with a way of thinking about this where everything has to do not with these ellipses and spheres in behavior space, but what we'll call the model manifold. And so that's a preview into the later part of the talk where I start talking about differential geometry. So in the end, I will connect fits to data to the renormalization group and continuum limit. Then I will start talking about a variety of applications in biology. And then I will turn to differential geometry, and that's a preview of the talk. Excellent and perceptive question. So we have this picture in condensed matter physics of emergence. We have complicated microscopic theories, most of whose details are important for the things that come up later. So our theory, Schrodinger's equation, basically underlies all of our theories of liquid crystals and superfluids and colloids and things. But we usually don't spend a lot of time thinking about Schrodinger's equation when we think about colloids and granular materials. And similarly, our theory of metals underlies our theory of superconductors. But for many purposes, you can use the Ginsburg-Landau theory or some effective theory of superconductors that doesn't rely on your detailed statements about the Fermi surface. And that concept that we have simpler descriptions partly comes out of simple continuum limits. That our theory of gases is basically just Boyle's law that involves large numbers of particles. But in some cases, we get a more interesting emergence that comes out, like crackling noise, out of a normalization group. So let me take two specific examples. Let's think of a model that a continuum limit is appropriate. Or microscopically, you have some kind of random walks, but macroscopically, you expect a diffusion equation. So if you have a microscopic model of a random walk, lots of different random walks are all described by the same diffusion equation. You can have phonons that are scattering off of density fluctuations in the material. You can have neutrons in a nuclear reactor bouncing off of strongly interacting nuclei in their vicinity. There are lots of different examples of this. And let's pick a model in which I have a hopping that can go to various sites in the vicinity. And after one step, you can imagine the model picks one of its neighbors 3 to one side or 3 to another side and equally likely hops in these different directions. That would be a particular model of diffusion with some 7 parameters giving the hopping probabilities. And we can ask, can you, after one hop, how sensitive is your fit to these 7 parameters? And of course, after one hop, you get a direct measure of these 7 parameters, and your spectrum of eigenvalues of this best fit, the dependence of the observed distribution after one step on the microscopic parameters, all the parameters can be measured perfectly well. It's not sloppy. But if you go to time 3, you get a very nice spectrum where some degrees of freedom are very easy to measure and some are very hard to measure. In particular, the mean position of this Gaussian depends upon the sum of these rates. And so if I change the sum of these rates, this is a sensitivity to parameter change, sensitivity to the changes of these rates. Any linear combination that changes the sum is very easy to measure. Any linear combination that changes the second moment is rather easy to measure. And then higher moments become harder and harder to measure. And so you can see, as you go to coarse grain to later and later time scales, if you insist upon thinking only on long length and time scales, you get the emergence of the continuum limit, where you would get a continuum equation which describes the behavior better and better at long time scales, and higher order gradient terms in the continuum limit becoming these sloppy directions. So sloppiness is the statement that if you look at something that's diffusing, you'll discover that it's very easy to measure the diffusion constant and the average drift. And it's almost impossible on long length time scales to deduce what the actual hopping rates are. My graduate students talk about how you may be able to tell from the sound waves certain things about the molecules in the sound, but the angle of the hydrogen atoms in the water molecule really are hard to deduce from sound wave measurements.
So should we think of this in terms of RG language as relevant and irrelevant?
That's the next one. The renormalization group. In particle physics, we also have this coarse graining, but there you need renormalization group. And I describe this as the microscopic details become unimportant for our practical universe, and that the high energy people would like to think that this is the interesting question, the fundamental underlying theory. When we do it, we find that everything becomes really boring and ugly and detailed when we look microscopically. The particle physicists, for some reason, their theories become more beautiful on higher and higher energy scales. But we share the fact that the details of the electroweak interaction are embodied in a few effective parameters in quantum electrodynamics. And in the end, that's why we need to build very big accelerators. It's that unless you actually look on those short length and time scales, you can't tell the difference between various possible microscopic theories. So you can take the same basic approach and apply it to the Ising model. We know the Ising model at its critical point has fluctuations on all scales. And we described that with the renormalization group. But now I'm going to ignore the fact that I know the renormalization group. I'm going to sit at the Ising model at its critical point, and I'm going to ask, how well can I tell the difference between the microscopic parameters of the Ising model and various rival models? So my rival models, like before, where I had hopping rates to different sites, now I'm going to add to the traditional Ising model a possibility of having bonds to sites far away. So I'll add second neighbor bonds, third neighbor bonds, and this very up to seventh neighbor bonds or something like that. And then I'll find eigenvalues, things that correspond to eigenvalues. These turn out to be there's a Fisher information matrix that comes from looking at the probability distribution of spin configurations and asking, if I change this parameter, how much does it change the probability distribution over all spin configurations? And you can measure that, it turns out, very coolly by looking at the 4-spin correlation functions in the Ising model. And it's a very, very cool calculation. But in the end, you discover that the Ising model is not particularly sloppy unless you coarse grain. So this is the Ising model. This is the external field. This is the T minus TC. And these are a bunch of other eigenvalues. And these two and these are separated, but these are all clumped together. That is to say, basically, you can look If you look at the near neighbor correlations, you can extract the fact that it's a nearest neighbor Ising model, and you can tell the difference between it and various rival models. However, just like the renormalization group suggests, if you look at the correlations only on longer distances, if you blur all the microscopic details, if you only care about long wavelengths, then you can do the calculation again with an even more sneaky way of doing force-spin correlations. And you get a beautiful separation into sloppy directions where these are the relevant directions and these are marginal and more irrelevant combinations of parameters. And the left eigenvectors of the Fisher information matrix directly tell you the combinations of parameters that change t minus tc and move along these various marginal and irrelevant directions.
You have, in your RG you say you have relevant, marginal, and irrelevant. In your description you have only stiff and sloppy.
Correct.
So the marginal are where?
These, I think, correspond
So they
to
are in
marginal.
between, so they are not in your classification, are they?
This method at the moment doesn't talk about flows, doesn't know about fixed points. It just says, give me a model, I'll tell you what parameters change the behavior along length and time scales. And those turn out to recapitulate what the renormalization group tells us. The renormalization group uses the small parameter that you're close to the critical point to tell you that this is natural. All I'm doing is saying, if you look near a critical point, you'll see this separation, and that separation. So it's a different window into the same physics. It's more general because I can apply it to systems biology. It's less powerful because I don't find out anything about scaling functions and.
I agree.
And
Just
things
my
like that.
argument is, where do the marginal stand? Are they stiff or are they sloppy?
In this case, they are among the sloppy directions. Yeah.
The previous example with diffusion was somewhat different because there the system forgets some details with time. And here, you just, for a fixed time, you just do coarse graining.
So here, it's equilibrium, so it's infinite time, and it's forgetting when you look at long length scales.
So it's...
So it's the same.
Equilibrium, you mean that T is above TC, or below? So if T is below
No, it's
TC,
equilibrium in the sense that I'm at TC,
you're right.
but I'm looking at the equilibrium ensemble and trying to figure out if I can tell that I've gone away. If I change these parameters, can I tell that the probability distribution is different? And the statement is, if I coarse grain and I look at those parameter combinations that don't change the external field and don't change T minus DC, those parameter combinations are hard to figure out. You have to move those in those directions a long way before you can tell that the behavior has changed. Which is self-evident. It's not a surprise. What's a surprise is that the same basic idea happens in all the rest of science. So this is where we came into this subject. We were looking at parts of science that like biology and maybe machine learning and economics, which we're looking at now, where you have relatively simple models, but maybe with several parameters. They're incomplete models. There are other parameters you know must be important that are ignored by these models. And these simple models succeed in describing macroeconomics, guiding the government in its monetary policy if the government actually paid attention to people who build models, and guiding Google in extracting information from the web, and guiding biologists in their exploration of use of theoretical models in guiding systems biology experiments. So here's our neural network model. I won't talk about some of these models because we're still working on them, but you can take digits and you can try to figure out from your neural network, this is the digit that went into the neural network. This is the model, the best fit for this neural network of this digit. And that space of all possible digits coming out of this neural network has some interesting structure. And in fact, if you look at so I guess I haven't told you about model manifolds yet, but you can see there's the same kind of hierarchy suggesting that the space of all digits, the subspace of all digits in the space of all possible pictures, is a low-dimensional surface and can be captured with few parameters. Okay, so now I'm going to...
Okay, can you elaborate a little bit on that, like, model? What kind of machine learning model are you using here?
You're asking me about vocabulary. This is something autoencoder, something, and my students know all of this, and I don't. There's so many different versions. So some neural networks, Charles may be suggesting or just interested in, some neural networks, you train them with data, and you get some signal out, and you're supposed to be able to recognize which digits there are. And some of them have this convenient aspect that the neural network acts as a way of predicting the digits, and some of them don't. And we picked one that does.
Right, so you're actually modeling the neural network's response to seeing that digit rather than the correlation between the different manifestations of that digit.
I didn't understand that.
Different ways of writing out that digit 1, for example.
I didn't. So we have a bunch of ones that we train this neural network on, and then we end up getting a 10-dimensional representation of what a 1 looks like, and that's a 10-parameter fit to the space of all 1s. And then we can look at that 10-parameter fit, and we can say, are all these parameters important, or are some combinations of parameters more important than others? And that's purportedly what I'm drawing here.
So when you say that you're training that network, you're actually using a synthetic network rather than doing some real, like, neural experiments?
There are no neurons in this neural network. Yes, sorry. Good point. Yes, I did not mean to misinterpret. Yes.
Because I thought it was doing the other way that
no actual neurons were abused in this neural network. Yes.
No, but I would imagine that you could also...
Let me move on. So, this was the original network that we got into the subject. It's a very cool network. It's very complicated. It's irritating. It's got all these proteins that I can never remember the names of. What's more embarrassing is that after so many years of talking to these people, I still don't know the names of the amino acids. And I'm constantly asking, what was that again? And he says, one of the amino acids. The big picture that Rick Serione, our cancer biologist, was telling us is that if you hit neuronal growth factor on the cell, you trigger this pathway and this pathway, and when it gets to the nucleus, it turns into a neuron. And if you hit it EGF, it goes to the receptor, it triggers this pathway and maybe this pathway, and it goes into the nucleus and it proliferates. And both of them produce ERK. NGF produces ERK that goes up and stays up. EGF produces ERK that goes up and goes down. And my colleague was saying that at the time it was thought that this side branch kept things up and that this side branch turned things down. For our purposes, we don't care about the biology. We just have this very large, complicated set of differential equations. And originally, I think my biology friends were saying, could you help us type in all those differential equations? We don't know how to do that. And we actually wrote a nice software environment to do that. And But the problem was, and my skepticism about this whole project had to do with these rate constants. That these are nonlinear differential equations, and these rate constants, there's 6 parameters just in this equation. I asked him, can you tell us what the numbers are? And he said, no. And I asked him, well, can you give us some range of parameters? And he said, well, I think I can tell you within a factor of 1,000. 1,000? 48 parameters within plus or minus 1,000 each. You know, I'd say it's not additive, it's multiplicative. It's a range of 1,000,000. And then I asked, well, okay, could you measure them, please? And he said he couldn't pay people enough to measure them because it was boring. And because, you know, they would waste 2 years of their life. And I said, well, how do you expect us to predict anything? And he said, well, he used to be able to predict things when it wasn't so complicated in his head, and it can't be that much harder on the computer. And sort of he was right.
But predicting using their rate constants, or...
He didn't have any rate constants. We had to make them up. And, you know, in the field, that's still done. They have 30 rate constants. These 10 are all Michaelis-Menten constants, and we'll set them all to this value we found in the literature. But they didn't measure 10. They measured 1. They set them all to the same number. And it doesn't matter.
Yeah.
It turns out it doesn't matter. And why, though? That's the interesting question. So the parameters, so on the one hand, I was right. You couldn't determine 48 parameters from 63 data points. We had 63 data points. This was a well-understood biology model. And they're right. It is well understood. You don't need these parameters, it turns out. But these are the range of the parameters that fit the data. Notice the best known parameter had an error bar of 50. That's a factor of 50. Okay? On the other hand, if you looked at these stiff and sloppy parameter combinations, there were a few parameter combinations that were well constrained, within a factor of 10%, factor of 1.5, factor of 2, and maybe all your predictions only depend on these things too, and then you could survive. If the predictions depended on these guys with error bars of 10 to the this is a million, then you would be unhappy. And it turns out you can make predictions. So here is our prediction for an experiment where we knock out this branch. And when we knocked out this branch, Rick Serione predicted that the EGF, which used to go up and down, would now stay up. And that way it would turn into a neuron instead of into a proliferation. And we tried it, and he was wrong. But our computer was right. Our computer predicted that it would go up and go down. And in fact, here's the experiment. This is a Western blot, and you can see that when you put EGF and LY, you still get it going up and going down. This is going up, and this is going down. And all the rest of it is just calibration that every biologist insists they be able to look at all the calibrations. So what does this mean? Well, it means that we had a 50-50 chance of being right, and we were right. What's the big deal? The big deal is you can make any predictions at all. These error bars represent parameter ensembles where the most well-determined parameter is varying by a factor of 50. And some of the parameters are varying. We really did an ensemble. We have all the parameters varying over factors of 1,000,000. And this is the error bar. And this is this picture that the stiff degrees of freedom are controlling the behavior. And these parameter combinations you can't measure also don't seem to matter for new experiments.
So are you able to identify those parameter combinations from from physics or from the dimensional analysis? How do you get those parameter combinations?
I will come back to that, but it's a very interesting question. If you have 48 parameters and and you know that only 5 combinations are important, is there some way of figuring out what the important combinations are? And the challenge is that you know that if you find 5 important directions, you can add sloppiness to any of them and find other 5 important directions. That the important directions are not well defined. The sloppy directions are confined. You can't add stiff to sloppy and get sloppy. You can add sloppy to stiff, and that gives you headaches. But there's a very cool method of taking this very large dimensional parameter space and reducing it that I hope to get to at the end. Okay, so these predictions are possible. These are other models. 17 models, wide variety of systems biology, did the same analysis for all of them. Notice 6 orders of magnitude in eigenvalue. That's 3 orders of magnitude in the ellipses. And actually most of these go down for another 6 orders of magnitude. You begin to get worried. So notice the most important parameter combination for this model, our model, is about 3 times more important than the next one, which is about 3 times more important than the next one. And 3 to the 48th is a very big number.
And Jimmy, you're saying there's always a separation. There's like some kind of a gap between.
I mean, at this point, I haven't explained why, but boy, it seems very common.
Yeah.
And it doesn't just have to do with biology. It has to do with fits to data. So here's the lambda CDM model for the early microwave background radiation. If you don't include the solar neutrinos and the BAO, I'm supposed to remember what that is, then you get this very narrow ribbon, which has a stiff combination. So by the time you're done with all these experiments, you get a really, really good constraint on that particular set of parameters. But there you have these dangerous sloppy directions, which really make it challenging to narrow down the parameter ranges along certain directions. And again, the sloppy spectrum. Other models, you saw a diffusion equation, the Ising model, radioactive decay. This is a neural network fit to stock market data. This is our cell signaling network. This is a Van der Pol oscillator. This is the circadian rhythms. This is quantum Monte Carlo variational wave functions. The best our best way of finding the energies of molecules, small molecules, is quantum Monte Carlo, and the variational wave functions underlying the quantum Monte Carlo are sloppy. This is the next generation particle accelerator. Okay, why is it sloppy? Well, I'm first going to tell you how to think about sloppiness, not in terms of eigenvalues and parameter space, which are plagued by the fact that you can change units and change everything. I'm going to go into data space where the error bars give me a natural metric. So think of a model with 2 free parameters, but it's a nonlinear model. So as you vary these 2 parameters, you traverse a space, a surface in prediction space. So naturally, I have 2 parameters. I'm going to only have a 3-dimensional prediction space. So I'm predicting this at 3 different times. But really, the space is large. And this is supposed to be like 48 dimensions. This is like 63 dimensions. This model manifold, notice, is coordinates given by the parameters. The other thing I want you to notice is it has edges. So this is the edge where one of the rates goes to infinity. This is the edge in which one of the rates goes to 0. And this particular model, when theta 1 equals theta 2, you get a fold line. Now, I should say these edges are interesting in 2 ways. On one way, they're pain in the neck. If you're doing some kind of search for the best fit, many of your searches will wander off onto this edge. And your computer will get unhappy, and you will never find the right fit, because once you're on the edge, the parameter is essentially gone. On the other hand, that's where simpler models lie. That a model with a 1 exponent and just a constant is certainly a simpler model. And the last thing I'd like to mention is that the natural metric on this space is given by the quality of the data. If I have a data point here, and this is the best fit in data space is just the Euclidean metric connecting the data, for the sum of the distances divided by the error bars is the natural distance connecting the best fit to the data point. And that is, and the induced metric, the metric tensor in this original parameter space induced by that is precisely this Hessian I've been talking about. So the eigenvalues of this metric in parameter space are the things I've been drawing on the board. Those are the eigenvalues about the best fit. I think to this audience I don't have to explain what geodesics are. If you take geodesics spanning away from the best fit, you can find geodesic coordinates. And the cool thing I want to point out, though, is that these long, thin valleys in parameter space, once you look in data space, become nice concentric spheres. And we have methods for using this insight to make better search algorithms for finding best fits. That if you could search for best fits in data space on the model manifold in its natural metric, rather than in parameter space, it would be a lot easier because you just go downhill. And that's in fact how Levenberg-Marquardt works, and we can make systematic improvements for this famous Levenberg-Marquardt algorithm by looking at geodesics.
So these are certainly not geodesics of spatial distance. So
this is geodesics in the model manifold, that is to say, the surface of predictions, this 48-dimensional surface in 63-dimensional space, has the shortest path between 2 points is the geodesic I'm talking about.
So it's still the shortest path measured spatially in that space.
In data space. So each little infinitesimal segment is summing the little least squared distances divided by the error bars squared. That sum is min. Now, what about this model manifold has to do with sloppiness? It turns out the model manifold is a hyperribbon. Hyperspheres you've heard of, they're high-dimensional spheres. Hypercubes you've heard of. I made up the term hyperribbon because I needed one. It's something which is, long and medium in width and thin, except higher dimensional. And this is the hyperribbon for a sum of exponentials. This is the hyperribbon for our diffusion equation. You can see it's got a long direction, but a very thin direction. And we quantify the fact that it's a hyperribbon by looking at the different stiff and sloppy directions from one point, sending geodesics to the edges of the model manifold and measuring the widths. And when we do that, we get a nice, let's see, the widths of the x's. We get a nice hierarchy where this is 20, and this is 10 to the minus 4. So you get a very strong hierarchy of widths, which corresponds beautifully to the square roots of those eigenvalues I told you about before. So the sloppy directions are not only sloppy in that you can, when you move a little ways along them, they don't change the behavior very much. If you move an infinite distance along them, sending the parameters all the way to infinity along a geodesic, they still don't change the behavior. And that is our geometric interpretation of sloppiness. It's a hyperribbon structure in model space. And that is parameter independent.
And you're saying that's what sort of generically systems go to?
Now, why does that happen? Well, it's very convenient for physics.
This is you're looking at sums of exponentials.
That was sum of exponentials. We've also done it for the neural network.
It's sums of 1 + 1 squared.
That's a linear model. It's also sloppy, but we don't understand that in terms of differential geometry because any linear model just becomes a hyperplane in the data space.
Linear, I guess it's something that doesn't fall exponentially.
I mean, I'm applying this also to systems biology models, which have all these Michaelis-Menten differential equations. It's not a statement about the way that exponentials fall off. It's nothing so detailed. Now, that doesn't mean that, well, I think that. I think I will not spend too much time on this. This is saying that there's a hierarchy of width and curvatures, because the next slide is more illuminating. But it turns out also the curvatures have a hierarchy. It's more complicated. Let me give you the key piece of why we think it's sloppy. And this is interpolation theory. So let's take a special case of a one-dimensional function fit by some nonlinear model. Now you know from interpolation theory that the more points you add, the better you can interpolate. What does that mean? Well, whenever I take a point and I specify the function at a point, that corresponds to take a slice of the model manifold. Remember, each dimension of the model manifold is a prediction, and each point in time is a different prediction. So if I take the set of all possible model, in my model, the set of all possible predictions consistent with these 4 data points, that corresponds to taking my original model manifold, slicing it along the axes corresponding to these 4 times, and looking at the remaining set of possible predictions. Second statement is that the convergence of this, the fact that you can determine the intervening points better and better, that corresponds to a hyperribbon-like structure. Each time I slice, each time I add a new data point, my predictions, the remaining spatial extent of my model manifold gets thinner and thinner. So that's the intuitive picture, that once I have enough data points to start constraining a function, it becomes a hyperribbon. We can do a little better by actually pulling out the theorem from the literature that tells you the range given a bound on the nth derivative of your functions in your model space. Then the range of possible predictions is given by this polynomial. If you call these delta t and you use the ratio test to determine the nth derivative, then you discover that the widths, as each time you add a point, the widths of the monomanifold are decreasing by a factor of delta t over r to the m, where r is the radius of convergence and delta t is the typical separation of points. That is to say, once you have one data point per radius of convergence, adding more data points is going to lead to the model manifold becoming hyperribbon-like, short, smaller and smaller. Yeah.
There's some assumption here of analyticity.
Correct.
We're looking for a fractal. This would fail.
I agree.
So,
Fortunately, most of these problems don't seem to be fractal. Also, chaotic dynamical systems. So 2 or 3 times we started to work on chaotic dynamical systems, we always get sidetracked somehow. So our Vanderpool oscillator paper was a start to doing a chaotic system, and we.
there's supposed to be an explanation with the assumption that the data and the models you use to fit the data
Are analytic. Yes.
Very strong assumption.
Well, the Ising model, it worked for the Ising model, But no, it's a strong assumption, but on the other hand, it is the assumption that underlies much of physics, much of science. You write down models that don't do bad things. I don't want to say that too strongly, that it's the dependence of the model behavior on the parameters that has to be analytic. So, for example, there's
The models, good.
there's some ecosystem models where every time you cross freezing, you shift your differential equation. I think our methods will work fine for that. Is the non-analyticity in the way in time is not so important.
Jim, I can see the thinness, but I don't understand why it still remains. I guess I'm missing. I can sort of intuitive, or this argument tells me that it becomes a ribbon-like, that it's becoming thin, but it still has this extension, right? The sloppy direction.
But no, the stiff direction is the long one in the model.
Oh, sorry. Yes. Okay.
Right.
Okay.
So there are a few. So the statement is there are some stiff directions.
Mm-hmm.
So before I have any data points, there's a stiff direction. I slice it once. So if I take a hyperribbon and I slice it in a random direction, chances are I'm not going to slice it in the perfect direction that keeps it long. It'll become short. I slice it again in a random direction. It becomes short.
Okay.
And the hierarchy of widths is the hierarchy of widths of the slices. Good question. Good. There are a bunch of questions I haven't answered. How am I doing on time? 5 more minutes. The bunch of questions I haven't answered. I haven't answered. One of the things that bugs me is our interpolation theory answer for why this works, and the renormalization group and continuum limit answers for why it works seem to be not very closely related. Okay? I guess there is a sense of analyticity. In fact, Peter Lepage was telling me that there's some key step in the operator product expansion where you assume analyticity in something or the other, and I haven't actually followed through on that, and I should. But this would be wonderful to try to integrate not only the behavior of the renormalization group and the continuum limit and systems biology, but also the explanation of why you get this hierarchy. The other question I think that's kind of interesting is that it doesn't seem clear that whether the reason every model we look at seems sloppy, it's possible we only look at successful models. How would you do science if all the microscopic behavior was important? Until you captured every last detail, you wouldn't be able to make predictions. And so most scientific models will select things that have low dimensional representations. And so I'm uncertain about that. I don't know whether to tell you science works because we only study problems that are sloppy, or whether I want to tell you that nature prefers sloppy systems. It's a little puzzling to me. Okay. So there are various things we've used our methods to do. Actually, this one is very cool, but I don't think it's sloppy, so I don't know why I put it in this talk. This one is our early work trying to say if the parameters don't matter, why bother measuring them? That's designed for people who are experimentalists. This one is a very interesting method of estimating systematic errors in interatomic potentials and things like that, density functional calculations. But this is the thing that I would recommend you ask me to continue with if you so choose, which is not my work, but Mark Transtrom's work, in which he used the geodesics to find simpler models, to do model reduction in a way that's that's almost automatic. Good, thank you very much.
I think an important question that you did not mention or provide a technical answer to is how do you practically calculate the eigenvalues? Because my impression is that you need to reduce certain things to certain kinds of quadratic forms.
You change the parameter a little bit to the right, you change the parameter a little bit to the left, you get an element in the matrix, and then when you're done, you diagonalize it.
So that still involves like some kind of linear or quadratic approximation.
Look. Trust me, I know how to do that. I mean, and in fact, we don't do it that way. We do it much fancier ways, but that's intellectually what I do.
So on your last comment, the model with 48 differential equations, it wasn't a model that was assumed to be simple. Yeah, so this suggests that the nature prefers sloppiness rather than we came with a simple model. But my question is more or less the same I tried to ask before: is what are those combination of parameters? Is there a physical way to understand? For example, when you do dimensional analysis, you get some important combinations. Yes, but is there a way to see from 48 parameters what are the good combinations?
Okay, so you asked that question before. I promised you an answer, and this is the answer. That was what I hoped somebody would ask. So the question is, if I have 48 parameters, can I find the interesting stiff directions in some systematic way? And in the olden days, I would say, I don't know how to do this. And part of the answer I gave before, that for every stiff combination, I can add an arbitrary superposition of sloppy directions and get another thing that looks just as good. That corresponds also to the fact that the eigendirections look like random noise. And this is the sloppiest eigendirection, but also the stiff eigendirections typically look pretty random. They're a couple that we have an interpretation for. Now that disturbs me because in the normalization group in the diffusion equation, the stiff directions made a lot of sense.
What model are you discussing here?
So this is the...
Whether it looks natural or unnatural depends totally on the diffusion. Whether you know how to write down the model in the right way.
So that's this model.
Oh, okay.
And if you can tell me that this combination, and there's a good reason to think this should be random and boring. It's sort of random matrix theory kind of ideas. But look. You're asking you're not giving me enough leeway. If you take that, and this is Mark Transtrom realized this when he took the geodesics along the sloppy directions and he went to the edge. He discovered that this eigendirection gradually turned in parameter space. It's a straight line in data space, but it moves in parameter space. It goes to infinity along a very simple direction. So we said before, the boundaries are simplified models with one less parameter. And this is telling you the parameter combination that you can drop.
So roughly speaking, parameters correspond to reaction rates?
So these two parameters might be a forward and backward reaction rate for a chemical reaction. It's not. It turns out it's a Michaelis-Menten numerator and a Michaelis-Menten denominator or something. But in any case, when these two go to infinity at the same rate, which is what's showing up here, that corresponds to a model in which the forward and backward reactions are in equilibrium. And if they're in equilibrium, you don't care about their rate. You just drop it and say equilibrium and put that as a constraint and run your model again. And what Mark did was he discovered that he could do that repeatedly.
So you will eliminate parameters.
One parameter at a time.
And you end up at the boundaries, is what you're saying.
And you end up at the boundary, you eliminate another parameter, you end up at that boundary, codimension 2 boundary, codimension 3 boundary, and he started out with this differential equations and this horrible network, and this range of parameters, and he ended up 36 parameters later with, not very sloppy, with a comprehensible diagram. You remember this was the side branch that kept the signal up, and this was the side branch that didn't matter, disappeared, and this was a negative feedback loop that I didn't show you because it was too complicated, and that's all that's left.
And how does he know that he cannot go further?
He tried, and when he did, the fit got bad. Now, it may be that there's some more clever method than just following geodesics to the edge to look for smaller manifolds, but this was enough to distill the original horrible model into something that looks comprehensible.
If it's ribbon like your 2 agents, how do you assign those?
He first of all, you can do both and figure out which one works better. And secondly, he has a criterion that locally tells him the direction that's closer to. You take the lowest two eigenvalue you take the lowest two eigenvalues and you decide which one is making them expand rather than contract, something like that. Yeah.
So this is nice, but actually I would expect more than that. So you suggested that there are few
I haven't finished.
combinations.
I haven't finished.
Okay.
The final equations, right? These are differential equations. There are fewer equations, right? So what happened to my original parameters? Which were the important parameters? Well, it turns out that the parameters in the reduced equation are explicit functions of the original parameters. So I can tell you, of your 48 original parameters, 12 parameter combinations that matter, and all the other parameter combinations you can ignore and get just as good a fit to the data.
Except for the fitting to the data, there's no direct way of measuring those combinations.
I'm sorry. You're right, there's a chicken and the egg. You first have to do the fit before you can do the reduced model. So you're not spared the original model. Also,
the experimentalist say the only thing I need to know is this thing.
No, the experimentalist isn't going to measure any of those constants either way. Whether you tell them it's important or not, they won't measure it. But you can at least say these are the important combinations, and then if the experimentalist says, I want to modify this, which one? PP2AA, whatever parameter in our equations are. I have an enzyme that can modify that. We'll say that's modifying theta 9 and theta 3 in this way, and we can make our predictions. So we haven't lost the microscopic details. It's like knowing the combinations of hopping rates that determine your diffusion constant. And then if you wanted to fiddle with the hopping rates microscopically, you would be able to tell how the macroscopic behavior. This is very cool. I'm very proud of Mark. And I wish he had thought of it just a little earlier. Yeah?
I have two questions. The first is, this procedure can tell you something more about the error of the parameters, of the 50 parameters.
Oh, sure. As I said, factor of 50.
Okay.
The best known parameter is a factor of 50 in this particular model. Now, that doesn't mean in the background radiation, the parameters are not well known. They have such good data. This is biology versus astrophysics.
Theory.
Pardon?
Theory. I mean, you can predict the genesis ahead of time.
Sure.
Theory is.
I mean, the theory is sloppy, and the data reflects.
The theory. There are always degeneracies.
Yeah. My job is to explore those degeneracies and understand them in an interesting way that allows me to give talks.
And my second question is, does this depend on the fact that you are using least square, or does it work also for other method like maximum likelihood?
So in the Ising model, we weren't doing least squared. We were looking at the natural metric between probability distributions. So our measure for distance was the was what's called the Kullback-Leibler divergence, or the Fisher information matrix. It was how likely this parameter set, the data generated by this parameter set, could have been generated by the other parameter set. That tells you the distance. And now you ask, if I use a different likelihood measure, I haven't thought deeply about that. I've had two existence proofs on either opposite ends of the spectrum, least squares and Kullback-Leibler divergence, and I'm sure there are other choices, and I'm not sure I can make the same argument for all of them. I just haven't thought about it.
How do you ensure that this reduced model actually covers all the range of parameters you started with?
Of course it doesn't. That the reduced model has forgotten some of the flexibility of the original model. And if you do a clever experiment, you can show the reduced model is wrong, and that may or may not tell you the original model is wrong.
But the original model with some parameter may kind of converge to a completely different simplified network. Right?
Oh yeah, no, that's true too. The simplified model, there's no guarantee that this model, if you have two different cell types with the same network in them, which is even much simpler than the real world, they may have different rates, and then you might get two different simplified models. Because this is just new. We've not sorted out the general case, and all those questions are interesting. So if I have different implementations, different data points, they will correspond to different simplified models, because they will potentially involve different directions to simplify. This early question: how do I know which direction to take in the thin directions? Clearly, a slight change in data will send me to the other direction. Greg?
You mentioned in passing random matrix models, or
random matrix
type,
so
which made me think of Wigner, which made me think of nuclear physics. Have you given your talk in front of nuclear physicists?
No, I haven't. That's a good question.
David notwithstanding.
We did spend a lot of time thinking about. In the early days, when we didn't understand what sloppiness was using the information geometry, we thought it might follow from a random matrix ensemble. And we recognized that what we were trying to describe was not just a linearization, but the nonlinear behavior. And that's captured by this. And we couldn't find a random matrix ensemble we liked. Random matrix ensembles give you very similar looking patterns, but not on a log scale. They give you these equally spaced eigenvalues on a linear scale. Ours are all scrunched down to the bottom. And so I have a slide someplace where I show you random matrix theory, and when we have 6 orders of magnitude, they have a bunch of eigenvalues all at the top.
Does that matter? Does it matter if you have a logarithmic variable or not?
Oh, I think that it's a clear indication that we're not described by the GOE ensemble. Now, there are a couple of random matrix ensembles that have exponentially distributed. So products of random matrices have like localization kinds of effects that give you that. We've looked at those too, and they have different statistics. There's subtle differences in the way things behave. And we don't really always have local repulsion. Even the basic feature of random matrix theory doesn't seem to be always or typically true of ours.
So in your eigenvalues, there are a few that are 100 times smaller than others.
These.
Why do you keep small eigenvalues? Why not to take,
Why not
3,
continue?
4, 5? Why?
So we stopped. He stopped here because his fit started getting worse when he removed any more parameters. So his procedure of removing parameters by taking the thinnest direction and moving to the edge stopped giving him good fits. That doesn't mean that this is the smallest possible one, but you remember I started with 11 orders of magnitude and came, and if we had started out in this field and saw 2 orders of magnitude difference between important and unimportant directions, we would not have been excited. modeling is complicated, some directions are less important. It was the 10 to the 12th or 10 to the 6th that bothered us. 10 to the 12th, you begin to worry about rounding errors, but at least the first 6 orders of magnitude were clearly there. Yeah?
Yeah. I'm absolutely fascinated by the biological applications here. And it strikes me that we may be seeing some, in biology, a difference from even cosmology, we may be seeing some implications of evolution. That an awful lot of what's gone on is leaving an awful lot of irrelevant, as you say, parameters or combinations of parameters behind. And so it begins to look to me like a qualitatively different kind of problem. Have you thought through that?
I would. This is a big deal. Then it turns out in the biology literature there's a concept called robustness, which was more or less started up by Stan Leibler, who used to be a theoretical physicist postdoc at Cornell, and then moved off to Rockefeller and started growing bacteria. Pardon? Oh, he did some time in Princeton. Okay. So biological robustness is the statement that organisms need to be able to survive fluctuations in their genome and fluctuations in their environment, and so they will evolve so that those kinds of fluctuations don't bother them. And so the idea is that all the parameters become unimportant in a robust network. So one of the statements I have is that each of these parameters, the 48 parameters, if I change it by a factor of 2, it screws up the behavior. Mm-hmm. That if I just change one parameter, if I just mutate that binding site, it's not robust. The second statement. Pardon? The
actual, the original model?
I think I've forgotten, certainly true of this model, the original model. The original model.
With the 48 parameters.
With the exception of these two, that even, I think I can move these without changing the behavior. But everything else is sensitive. And I think we checked it for all of the 17 biology models that we looked at.
Sir, the original model you say is not robust.
It's not robust.
But
it's sloppy. There are a few parameter combinations that are important, but they're not parameters.
Yeah, they're in some direction.
They're in some rotated space, so that every parameter, if you change it alone, screws up the behavior. The other half of that is that we took all of the examples.
So biology has no way of being sloppy on itself.
Well, at least our model of biology. I think sloppiness in biology, robustness in biology, the examples that they've come up with, most of them can be explained by sloppiness. That they have some network with 100 parameters, and they vary. Theoretical model.
But this is not biologically sloppy.
Correct. No, it's sloppy. It's sloppy. It's not robust.
So I think there's
it's sloppy. It's not robust. It's got lots of directions, but the directions that hold the behavior.
But isn't sloppiness, biological sloppiness, would be the ability to make changes without destroying?
If I change this and this and this in the right way.
Mutations aren't going to do that.
Correct.
So it's not biologically sloppy.
It's not biologically robust. Sloppiness isn't a statement you can change parameters. Robustness is.
I understand. But sloppiness would.
Oh, you're saying sloppy, you want to use sloppiness to say the behavior doesn't change under mutations.
Yeah, there are some changes.
I guess.
Biologically make, which.
You're using the term sloppiness in a legitimate way. It's just not the way I would choose to use it.
Sloppiness is a third word method.
Yes.
So I can use it anywhere else.
You can, and I can object.
But what you're describing is not correct. There's a difference between the sloppiness of the biological sense, where you can only make local mutations or individual and sloppiness of the model and the data.
Right.
You're saying that this model in the data is sloppy. combinations of local mutations don't affect the result.
Yes, yes.
So the function is robust under non-local changes.
Certain non-local changes, but not all.
Biological. So biologically, this is not stopping.
For biological, in the directions that biology can change things, which I would argue, we have this concept of chemotype. There's a phenotype and a genotype. The chemotype is the set of reaction rates. And in the chemotype space, the natural dimensions that you mutate are along these rate constants. A typical mutation will change one rate constant or maybe two. And in that chemotype space, the bare coordinates typically are the ones that you can mutate along, and they don't preserve the behavior.
So what your analysis does not suggest anything about biology in the way that works.
Yeah. There's a lot of attention along the Jim Langer's point of view about different kinds of robustness, and I guess unfortunately I have to say we looked into that in great detail. We wrote a paper on it and reviewed the literature, and we came to the conclusion by detailed calculations that most of the examples that people had come up with showing that things were robust could be explained one way or another by the fact that the models that they were using were naturally sloppy.
Biologically available software?
No. So one of the models, for example, there's a model of embryo development or something like that, in which they built a model and then they varied all the parameters by factors of 10, and 2% of the time they got the same behavior. And they said, think of a 100-dimensional cube. I'm varying things by a factor of 10. Isn't it amazing? Do I have a figure of this? It would be natural. So if you assume that all 100 parameters matter, then it became an amazing coincidence that no, I don't have it here. But if you have only 4 or 5 parameters that matter, then the 2% probability turns out to be a pretty nice subregion. And we actually worked out the details for their model and drew the pictures, and it looks entirely plausible that you wouldn't change the behavior just because the model is sloppy and not because it has particularly poorly defined stiff directions.
Put it another way, if you took that model you ended up with at the end,
Yep.
the truncated one that works so well, I mean, is that biologically realizable? Could it be that evolution?
Does some
Yeah, could you imagine that this was an stage?
Could you imagine why did the organism actually have all these extra degrees of freedom? That's an important, interesting question. And first of all, I don't understand the biology well enough to answer good questions. Secondly, I think a lot of these proteins are involved in several different things. So the fact that there are other proteins here may be important for regulating this in some other way. Eric Sigia has a model of evolution of these networks, which, you think, this is bad engineering. Why have all this jury-rigged stuff? And when he does his evolution of networks, he gets things that look jury-rigged too. And so it may be that this is one of those few cases where biology hasn't fine-tuned things to be as perfect as possible, and in fact everything's sort of hokey and thrown together.
My understanding is that what usually happens is that you have some biological mechanism, and then by accident it gets used for a different
Yep.
purpose altogether, at least the parts of it that are relevant to that other
Yep.
purpose. And so, if you,
So it's not a surprise that it looks kind of jury-rigged, yeah. Oh, I need a new fan belt. I don't have a fan belt. Oh, I see here a bicycle chain. Let me use that. Yeah. Yeah. Perhaps I should let people go. Thank you very much.
Well, thank you.
Happy to talk more.